All right, let's go.
Number 12, the first warning sign. In 1986, 7 astronomers published results that should not have been possible. David Bernstein, Roger Davies, Alan Dressler, Sandra Faber, Donald Lindenbell, Roberto Turlevich, and Gary Wegner had spent years measuring the distances and velocities of hundreds of elliptical galaxies, using a technique that compared a galaxy's brightness to how fast its stars were spinning. The method let them calculate how fast each galaxy should be receding from us if the universe's expansion were the only thing moving it. The numbers did not match. Galaxy after galaxy was moving faster than expansion alone could explain, and all of them were drifting in the same general direction, toward the constellations Centaurus and Hydra. Something with enormous mass was out there, pulling on everything nearby, including us. The team became known in the literature as the Seven Samurai. The thing they had found a shadow of without ever seeing it directly, they named the Great Attractor. It was not a small deviation. The local group, our galaxy, Andromeda, and everything gravitationally tied to them, was found to be moving relative to the cosmic microwave background at roughly 630 kilometers per second, 1,000,000 miles an hour. Every single galaxy nearby was being carried along with it, and nobody could point a telescope at the thing responsible and see it. That absence, a measurable force with an invisible source, is the entire reason this mystery has survived 40 years of astronomy without ever fully closing. Number 11, the invisible wall. The reason nobody could simply look is built into the geometry of where we live. The Great Attractor sits almost directly behind the disk of our own galaxy, in a band of sky astronomers call the zone of avoidance. Stars, gas, and thick lanes of dust from the Milky Way itself sit between us and it, blocking out roughly a fifth of the entire sky in ordinary visible light. For years, that meant the most important gravitational structure in our cosmic neighborhood was effectively invisible. Astronomers had to build entirely new ways of looking. In the 1990s, teams using Australia's Parkes radio telescope, the same dish that helped relay footage from the Apollo missions, pointed a specially built 21-centimeter receiver directly into the zone of avoidance. Radio waves pass through dust far more easily than visible light. What they found were hundreds of previously uncatalogued galaxies, sitting exactly where theory said mass should be concentrated, hidden in plain sight behind our own galactic disk the entire time. Infrared surveys and X-ray telescopes added more of the picture through the 2000s, but every single one of these techniques is still working around an obstruction, not through one. Nobody has ever taken a direct optical picture of the Great Attractor's core the way we can photograph a normal galaxy cluster. Every map of it is a reconstruction, assembled from radio signals, X-ray glow, and the motion of galaxies we can see nearby. Never a direct image of the thing itself. Number 10, the cluster that wasn't enough. Once astronomers could partly see through the fog, they found a real, physically massive object sitting almost exactly where the pole was strongest. The Norma cluster, cataloged as ACO 3627, roughly 250 million light-years away in the direction of the constellation Norma. X-ray observations through the 1990s and 2000s confirmed it as a dense, evolved cluster full of old galaxies, many of them colliding with their neighbors and radiating heavily in radio wavelengths, exactly the signature of a massive, gravitationally settled structure. For a while, this looked like the answer. A real object, a real location, a real mass. Case closed. Except the mass never added up. The original 1988 estimate for the Great Attractor's total gravitational influence put its mass at roughly 5.4 times 10 to the 16th power in solar masses, a genuinely staggering figure. Later infrared and X-ray studies revised that number downward by close to an order of magnitude once astronomers accounted for how much of the original signal was actually the Norma cluster itself. Even with the revision, the Norma cluster alone was still short of what the observed motion required. We had found a real thing exactly where we expected it, It simply was not big enough on its own to be the whole story. Number 9. The missing mass. The shortfall between the visible mass in that direction and the mass required to produce the observed motion points toward the same invisible culprit behind the most of the universe's large-scale structure: dark matter. Current cosmological measurements put ordinary matter, everything that makes up stars, planets, gas, and us, at only around 5% of the total mass energy of the universe. Dark matter accounts for roughly 27%. The rest is dark energy, which is busy doing the opposite job, pushing everything apart. Dark matter does not emit light, does not block light, and has never been directly detected in a laboratory. Every piece of evidence for it comes from exactly the kind of effect the Great Attractor represents: visible matter moving as though something massive is nearby, when nothing massive is visible. Galaxy rotation curves, gravitational lensing around galaxy clusters, and the large-scale flow of galaxies toward the Great Attractor are three of the strongest lines of evidence physicists have for dark matter's existence at all. Which means the honest description of what's out there is this: we are being pulled, at a speed we can measure to the kilometer per second, to a structure that is mostly made of a substance nobody has ever seen, confirmed only because everything visible near it is moving in a way that only makes sense if something unseen is holding it together. Number 8. A valley, not a point. In September 2014, R. Brent Tully and an international team of collaborators published a paper in Nature that changed how astronomers even describe the Great Attractor. Rather than treating it as a single object sitting at a single coordinate, they mapped the motion of tens of thousands of galaxies across an enormous volume of the local universe and defined something they called a basin of attraction, a region where every galaxy's motion, no matter where it started, eventually curves inward toward the same general low point, the way water flowing across a landscape eventually finds the bottom of a valley. That basin turned out to be enormous, 500 million light-years across, containing the combined mass of around 100 million billion suns, spread across roughly 100,000 galaxies, including our own. The team named the whole structure Laniake, Hawaiian for immense heaven, and confirmed that the Great Attractor sits at its gravitational low point, not a single body, but the deepest part of a gravitational valley the size of a supercluster. This reframing matters more than it sounds like it should. It means the question, what is the Great Attractor, was slightly the wrong question all along. It was never necessarily one thing waiting to be found. It may simply be the coordinate where the gravity of an entire supercluster's worth of galaxies, clusters, and dark matter happens to converge. Number 7. Hidden layers. The Norma cluster is not the only structure sitting in that direction. Deeper in the same general line of sight, still partly obscured by the same zone of avoidance, lies the Vela supercluster, a large structure astronomers only began mapping in detail through infrared and X-ray surveys in the 2010s, and one that is still being outlined today. Other filaments in smaller clusters sit layered behind it, each contributing a share of the total pull, none of them individually large enough to account for it all. This is where the story gets genuinely uncertain, rather than just technically difficult. Some analyses treat the Great Attractor as effectively synonymous with Laniake's basin of attraction as a whole. Others argue that what we call the Great Attractor may be several distinct overdense structures stacked behind one another along nearly the same sightline purely by coincidence, that together produce a gravitational signal we've been reading as a single source for 40 years. If that's correct, then there was never a single door to open. The name may describe a direction more than a destination, a label given to whatever combination of clusters, filaments, and dark matter happens to sit along the one patch of sky we cannot see through. Number 6. The hidden push. In 2017, a team led by Yehuda Hoffman, working with Daniel Pomered, Brent Tully, and Helene Courtois, published a finding in Nature Astronomy that reframed the picture yet again. Using peculiar velocity data from galaxies across the local universe, they identified a massive underdensity, a region containing far less matter than the average patch of space, positioned almost exactly opposite the Great Attractor's direction on the sky. They called it the dipole repeller, Empty space cannot actively push anything, but relative to everything surrounding it, a region with less mass behaves like a repulsion because the denser regions on every other side keep pulling matter away faster than matter falls in. The local group's total motion of roughly 630 kilometers per second towards Centaurus and Hydra, it turns out, is not purely a story of attraction. Part of it is flight. We are being pushed out of a void behind us at nearly the same time we are being pulled toward density ahead of us. That distinction is not just semantic. It means decades of measurements describing the strength of the Great Attractor's pull or quietly measuring the combined effect of two entirely different phenomena the whole time, one made of something and one made of almost nothing. Number 5. The Bigger Attractor. Roughly 3 times farther away than the Great Attractor sits the Shapley supercluster, first identified by astronomer Harlow Shapley in the 1930s and confirmed decades later as the single densest concentration of galaxy clusters in the entire local universe. Multiple independent studies have since found that Shapley's gravitational pull on the local group is comparable in magnitude to the Great Attractor's, despite sitting nearly 3 times farther out, which means its actual mass has to be dramatically larger. Some researchers now describe the relationship between the two structures directly. Shapley's gravitational reach is large enough to entirely subsume the flow historically attributed to the Great Attractor, meaning our galaxy may not ultimately be falling toward Norma and Laniakea basin at all, but towards something several times more massive on the far side of it. Tully's own team, after publishing the Laniakea paper, noted that our local group appeared to be moving toward Shapley, raising the possibility that Laniakea itself might be nothing more than an outlying arm of an even larger structure, in Tully's own description, more like the trunk of an elephant than the whole animal. If that's the correct picture, the Great Attractor was never our final destination. It was a waypoint. A real gravitationally significant structure that happens to sit directly between us and something several times its size, close enough to distort our reading of everything beyond it for the better part of 40 years. Number 4. Beyond the Universe. In 2008, Alexander Kashlinsky at NASA's Goddard Space Center published a measurement stranger than anything discussed so far. Using an effect called the kinetic Sunyaev-Zeldovich effect, essentially measuring how the cosmic microwave background's temperature shifts slightly as it passes through moving clusters of hot gas. His team tracked the motion of more than 1,000 galaxy clusters, some more than 2.5 billion light-years away. Far beyond any distance the Great Attractor, Laniakea, or even Shapley could plausibly influence gravitationally. The clusters were still moving in a broadly coherent direction, roughly aligned with the same patch of sky as the Great Attractor. Kashlinsky named the effect dark flow and was explicit about what it could mean if confirmed. Whatever is causing motion on that scale might not be inside our observable universe at all. It could be the gravitational relic of structure from before inflation, or evidence of mass sitting beyond the cosmic horizon, the boundary past which light simply has not had time to reach us since the beginning of the universe. The claim remains genuinely disputed. The Planck satellite team reanalyzed cosmic microwave background data years later and reported no statistically significant dark flow signal, directly contradicting Kashlinsky's result. Kashlinsky and his collaborators pushed back on the methodology of that rebuttal. Neither side has produced a decisive enough result to end the argument, and the dispute remains unresolved heading into 2026. Number 3. The Unfound Bottom. The most recent work on this problem doesn't come from a new telescope, it comes from machine learning. Researchers have begun training convolutional neural networks on cosmological simulations, then applying those trained networks to reconstruct the local universe's velocity field at far higher resolution than older statistical methods allowed. Specifically built to see non-linear structure, the older reconstructions smoothed away, including structure hidden inside the zone of avoidance itself. When one such reconstruction searched specifically for the Great Attractor at the coordinates where Laniake's basin was expected to bottom out, the signal was weaker and more diffuse than anticipated. The researchers' own conclusion was cautious but striking. If the attractor isn't cleanly detected exactly where expected, that doesn't mean there's no overdensity there. It may mean Laniake itself is only a smaller basin nested inside a larger one, with its true gravitational center sitting somewhere we haven't correctly located yet. 40 years after the Seven Samurai, in other words, the most current analysis available doesn't converge on a cleaner answer. It suggests the structure may be one layer deeper than even the 2014 Laniake paper assumed, that we may have named the wrong valley or found only a smaller basin inside a far larger one whose true center remains unmapped. Number 2. The Unreachable Destination. Here is the part almost nobody expects. Despite everything pulling us, we are not going to fall into the Great Attractor, ever. The reason is dark energy. Laniakea, the basin containing the Great Attractor, is not gravitationally bound the way a single galaxy or tightly orbiting cluster is. Calculations of the local group's actual peculiar velocity, the part of our motion not explained by cosmic expansion, show it running at only around 20% of what would be required to gravitationally bind us to that structure permanently. The pull is real. It is nowhere near strong enough to win. For the next several billion years, the Great Attractor's gravity will keep bending our trajectory, slowing our recession from that region compared to galaxies on the opposite side of the sky. But the accelerating expansion of the universe, driven by dark energy, does not relent. Eventually, the distance will grow faster than gravity can close it. The Great Attractor's influence will fade past relevance, and the Milky Way, already committed to a much closer, much certainer merger with Andromeda, will simply drift on, never having reached the thing it spent its entire measurable existence falling toward. Number 1. A mystery that never closes. Every theory on this list is still standing at the same time. The normal cluster is real but insufficient. Dark matter almost certainly makes up most of the missing mass but remains fundamentally undetected. The dipole repeller genuinely pushes as well as pulls. Shapley genuinely appears to dominate at greater range. Dark flow may or may not extend past the edge of everything we can observe, and the newest, most advanced reconstructions we have suggest we may not have even located the true bottom of the gravitational valley we've been mapping for 40 years. None of these theories individually disprove the others. That is the part that makes the Great Attractor different from most solved mysteries in astronomy. It was never a single question with a single hidden answer waiting behind better instruments. It is a genuinely layered problem, a wall we can't see through, hiding a mass we can't fully account for, sitting in front of a larger mass we've only recently started to suspect, possibly connected to a flow that might not even originate inside our universe. We named it before we understood any of that. We have been measurably, provably moving toward it for as long as we've known it exists, at over 1 million miles an hour, without ever slowing down to wait for the answer. And now we know, with more certainty than the Seven Samurai ever could have had in 1986, that we are never actually going to get there. Dark energy will carry the destination out of reach long before we close the distance. We spent 40 years chasing something we will never arrive at, built almost entirely out of things we still cannot see. Subscribe to Cosmic Hives. See you in the next one.